Hello everyone. Today our review practice is going to be on the review notes for limits and some practice problems. All right, so first things first, the notation for a limit. The limit as x approaches c of f of x equals n. That's just strictly whenever you see this notation, you know you're evaluating a limit. And what that means is as x gets close to some number c, y gets close to some value n. In other words, as we plug in values that get close to c, our y values get close to n. A limit is a y value. Now, to find a limit, we can graphically look at a picture, or we can evaluate that limit algebraically. This is what we focus on mainly in this course. Basically, you just plug c into the function. If you get an answer, that's the limit. If you don't get an answer, we have to do a few things, right? If it's a fraction, we factor and try again. If it has a radical sign in it, we're going to rationalize, and sometimes we're going to deal with complex fractions. So you should be able to, after you practice the review sheet, work through these different types of things. After you simplify your function, if you plug your c back in, get an answer, that's the limit. If you don't get an answer, the limit does not exist. Up here, all I did was more specifically show the notation if we want to evaluate a left limit, if we want to evaluate a right limit, and that will be clear in any given problem. So, this is just a little bit of review on the notation. One of the things we talk about when we're dealing with limits is continuity. So this is our continuity checklist. Remember, plug in the number, get an answer. Evaluate the limit at that specific value, get an answer. If those two numbers match, right? If the limit and the function value are the same, that means our functions are continuous. Types of functions that we look at when we're trying to determine continuity, basically rational functions and piecewise functions. If a function is not continuous, you can have a hole or asymptote at that point of discontinuity. Remember, if it's a hole, that means the limit exists. If it's an asymptote, that means the limit does not exist. And pretty much the last thing we talked about in this topic are how to evaluate limits to infinity. Remember, when we're evaluating a limit to infinity, we're dealing with the end behavior. It's the same as when we studied horizontal asymptotes in our rational unit. Okay. You look at your function, compare the highest degree in the numerator, the highest degree in the denominator. If the top is greater, it's top heavy, our limit goes to positive or negative infinity. We have to do a little work with that one. If the top and the bottom are equal, it's a ratio of the coefficients. And if the top is less than the bottom, the limit goes to 0. And again, I'm going to do a problem to kind of review this. So if you take a look at your review sheet, I kind of circled the problems I want to go through. So if we take a look at number 3, the limit as x approaches 2 of 8x squared minus 4. Basically, when we see this notation, we know just plug in the number. And again, if you need to use your calculator for this, feel free. I'm not going to make an issue out of that here. It's 8 times 2 squared minus 4. And your answer here is 28. And that's that. Let's take a look and see what happens with number 6. So number 6, I have the limit as x approaches 4 of x squared minus 16 over x minus 4. This is a rational function. So usually what I do, I just take and I see what's going to happen in my denominator. When I plug in 4, I'm going to get a 0. That's undefined. So I know I have to do more work with this one. So I go back to my expression here. And I say, oh, we can factor this. Factor, simplify, and then I'm going to take my number and plug it back in. And please don't ask if you can use a calculator for that one. I hope you can do that. You have your fingers. And there's your answer for that one. Now, had we done this and got another 0, then that limit would not exist. Let's take a look at number 9. The limit as x approaches 3 of x plus 3 over x squared minus 9. Again, we're going to take our number and just do a little quick check. 3 squared 9 minus 9, 0. Factor. Simplify. And try again. Now when I go to reevaluate this and I plug in 3, I get 1 over 0. Since I get a 0 the second time, this limit does not exist. Now, before I move on to number 10, I just want to mention, I'm not going to be doing 11 and 12 with you. I want you guys to practice those on your own. You're going to have to rationalize. So if you're having trouble with that, my solutions will be posted. But, please give them a shot. Number 10. The limit as x goes to infinity. Now this is different. I'm not thinking about when my number gets close to some value. I'm thinking about what's happening on the ends. So here I'm going to take the term with the highest power in the numerator, the term with the highest power in the denominator. And I see my top power is higher. So this means I have to think about what's going to happen as I plug in really big numbers. Okay? Remember, your answer is either going to go to positive infinity or negative infinity. It's whatever sign you would get in. So if I plugged in a really big positive value and cube it, my numerator is going to be a positive number. If I plug in a really big power in the denominator and square it, I'm also going to get a positive. So this graph is going to infinity, right? So it means it would be kind of going like that at the end of the graph somehow. Okay, that's all. That's all you have to do. Okay. In the next section, numbers 15 and 16, this is evaluating piecewise functions. You're going to be evaluating left and right limits and determining if your function is continuous. I want you to be able to practice both of those, so I kind of made a different problem for this. So let's say we're being asked to evaluate limits with a piecewise function. I would give you the function, and I would maybe ask you to find f of 0. Well, f of 0 is going to be 2. Now, if I ask you to find the limit as x approaches 0, when we're given a piecewise function, you guys should know that you've got to break this up. You have to evaluate the limit as x approaches 0 from the left of f of x and the limit as x approaches 0 from the right of f of x. Now, if I go back to f of x, I have to think about, well, what would I evaluate? Well, if I'm less than 0, that's my left limit, I'm going to be plugging into this function. And if I'm approaching 0 from the right, that means I'm in this section. So I would evaluate 0 in that function. When I plug in, I get 2. When I plug in, I get negative 2. Since these values don't match, my limit does not exist. And if the limit does not exist, that function cannot be continuous. Okay, so that's an example of how to evaluate one-sided limits and determine if something is continuous or not. If all 3 numbers matched, then this function would be continuous. The last thing I want to do is real quickly just go over some of the graphing problems. So if we're looking at the graph of a function and we're being asked, I'm going to probably just do D, E, and F with you. So D is f of 2. E, the limit as x approaches 2 from the left. And F is the limit as x approaches 2 from the right. So if we want to answer these questions, and we're looking at the graph of our function, f of 2 means I want the function value of 2. If I'm looking at my graph and I want the function value, I'm just going to go to 2 and look for the closed-in circle. So f of 2 is negative 3. Now if I want to evaluate the limit as x approaches 2 from the left, again, I go to the left side of 2 and I say, what happens as I plug in numbers that are getting closer to 2. What's happening to my y values? They're getting closer to 0. The limit as x approaches 2 from the right. Again, what's happening to my y values? They're getting close to 0. Okay. If I was asked to find the limit as x approaches 2, since these two numbers are the same, that's going to be the limit. Now, usually it's very easy to see that the limit is a whole. The whole is going to be the value, the y value of that limit. Okay. I hope this video was helpful. As always, you can go back and look at review sheets from the, when we took the test. But I just wanted to kind of refresh your memory and give you a little, taste of what your final is. Goodbye.